Thank you. Thank you very much, Sarah, and thank you for all the organizers. So I'm very excited to be in this fantastic place, and I'm really looking forward to discussion. So thank you. So today I will discuss some not so recent work we did during the PhD of Mette Demir-Sigil. I will give the name written down later. And so there is many words in this title. Maybe the most important one is the first one, simple. And I will advocate today for simple models. So I don't mean all models must be simple. It's not my, but for this collaboration, we were lucky enough to have let's say a simple yet original experiment which can be transcribed into simple hypothesis and simple mathematical model. And when it is simple, you can take advantage of that. And this is something I like to insist on today. So this model is about the expansion of a cell colony. So it will be a question of a wave, of expansion as a propagation of a wave. So very simple mathematical object. We are looking for something which is stationary in some moving frame, like in reaction diffusion equation. It will be very much related to reaction diffusion equations in ecology. So it's about an expansion, and due to some motion toward oxygen, which again is very classical for bacteria, let's say, but this is not about bacteria today, it's about Dictyostelium cells. Anyway, and this model will be made of two behaviors. Cell, as you will see in the model, will either move, so they will go, or they will divide, they will grow. And the combination of these two things, these two very basic behaviors, makes the story quite interesting in my own opinion. So as I said, it will be about PD models. There will be a very macroscopic PD. It's possible to discuss later more mesoscopic or microscopic description, but for today I will stick to the very broad macroscopic level. It will be a matter of waves, and the question is about collective motion, along a self-generated gradient. This is something I've been interested in for a very long time. This is a case where you have expansion or collective motion of a population of cells, and they make their own environment dynamic. In fact, they create or they shape some gradient by consuming some or producing some chemicals. And by doing so, they generate signaling gradients, and they move along those gradients. And in fact, so you have a feedback between the population and its environment. And this feedback is something which I think is quite interesting. And the experiment I will describe today is a very simple example, let's say, of this process of self-generation of a gradient. And as I said, it will only be about a very simple macroscopic model, so no kinetic equations today, although it could be relevant, but again, it was not necessary for the collaboration, let's put it this way. And I think it's already quite a lot of material at this level. So let's start with a very sort of warm-up with one equation, which is not the equation I'm interested in, but a variant of this one, which is a celebrated Fisher equation, also known as the Fisher-Kolmogorov-Petrovsky-Piskunov, or they propose a nice mathematical statement about that. So it features two phenomenon, very simple ones. So diffusion of cells. So think of rho of being a cell density. You have some dense cells which are in some environment with some density rho, which is a function of t and x. And you have diffusion of the cells, so they move randomly without any preferred direction. And they grow with some rate. So you have two coefficients, d and r, and with these two things you can build a speed by homogeneity of the coefficients. So this geometric mean, square root of rd, is a speed. And if you double it, you have actually the speed of expansion of a population according to these two effects of diffusion and let's say cell division or increase of the number of individuals. So you have a wave, and this is really the basis of many models of population expansion. For example, this is a pine beetle in France, as you can recognize. And for experts into reaction diffusion equation, they know that it's actually a minimal speed. You can have faster waves, but I will just consider this as my my object, and I will just I will just ignore speed which are faster. So this will be the speed of expansion for this model, like in this simple picture. So this is very much very well understood. But keep in mind this formula, root of RD, which is a speed of expansion. It's not completely trivial because if you have, for example, you need both. If R is 0, of course, there is no speed. This is 0, and of course, there cannot be a wave with a linear speed because it's only diffusion, and diffusion is much slower than that. It's just let's say move macroscopically at the rate root of t. So this is very slow, let's say, and of course you need motion, you need diffusion to make a wave. So you really need both. Okay, so now what about the experiment? So let me show you the movie first, and then I will explain the experiment. So some of you have already seen this work, and I apologize for that, but I hope maybe the perspective is slightly different. Okay, so I hope this works. So I don't explain the setup, but I show you the result first. So you have each you can see cells by eyes. So these are Dictyostelium, discoideum, very well studied, very much studied, but not exactly in this context. It's part of the originality of this work is to put Dictyostelium in a different, let's say, medium than usual. Okay, so you see cells, and you see this remarkable ring of cells that is expanding towards radially. Okay, so the question biophysicists asked is to understand that. And one way to understand that, for example, is to compute the speed. If you're able to compute the speed through mathematical modeling, it means that you have somehow, let's say, unraveled in some sense the phenomenon, and it's possible to understand it. So, of course, if there is any question, please do not hesitate to interrupt. Yes. What do you mean by the back? These ones? Ah, good question. So as you notice, it's very good point. They don't have the same behaviors. If you look at cells, if you look at the surrounding cells, they seem not to move, or they hardly move. At least if you focus on one cell, clearly the motion of the cell, of an individual cell, do not explain this radial expansion. This is for sure. I will come back to that later. This is part of the modeling, is to try to see what each individual cell is doing and what is the collective behavior, of course. Okay, so this is the result. And now is the experiment, the experimental setup. So you have a plate with some medium, which is not very rich, not very poor. Cells can divide, but it's not a rich medium. And initially, as in the movie, you have an initial, let's say, drop or layer of cells in green, and you put a cover glass, which is not permeable to oxygen, which is its main feature, and you put it over the plate. Okay, so you don't squeeze the cells, but it's a very narrow medium now. The space is very narrow, and so it's a confining experiment. You confine the cells between the plate and the cover glass, and the main outcome is that oxygen will be only available laterally. Okay, there will be absolutely no oxygen coming from the top due to this cover glass, and this is it. It's only so it's very low-tech experiment. It seems to be very easy to do. And what you observe is what you have seen in the movie, is that after some time you see a ring of cells which is expanding, and I will show you later. It's a perfect wave. It's really moving at constant speed for a very long time. It's a very remarkable pattern. Okay, and why? So this is all what I will speak about. Mainly due to this work with biophysicists Olivier Cochet-Escartin, Christophe Anjar, and Jean-Paul Rieu, and colleagues of them. And why did they do that? So this we didn't invent this setup. It was apparently first proposed in 2018 in Lyon as well. You can see the proximity in a cancer research lab, and the idea is to design something which is easy to make, where you can observe the cells in the core of your colony, where oxygen is very low. Okay, and the idea is to experimentally design an environment, a medium, which is at ultra low concentration of oxygen, so that you can look how cells react to very low levels of oxygen, which is something which is interesting for oncology, where people think that in the tissues, at some stage, there are actually very low concentration of oxygen. It can happen. For example, you can think of tumor or in embryology as well. But if you want to do it in a controlled way, it's very, very complicated to make. So during this collaboration, I've been visiting the lab of my colleagues, which are in the next building close to the mass department in Lyon. And they were actually doing control experiment with control oxygen level and oxygen gradient. And there was gigantic nitrogen bottle, because you have to pump nitrogen at a very high rate to maintain your microfluidic channel at a very low oxygen level, if you want to do it in a controlled way. But this setup is doing that naturally, because all the cells, as you can imagine, all the cells in the ring, they consume oxygen. So oxygen is consumed at the level of the ring. It diffuses very fast, and this is the reason why it's so complicated to do it in a controlled way in microfluidic experiment. But still, it's diffusing very fast, so all available oxygen diffusing from the lateral side is consumed by the ring or the surrounding cells, which I have not depicted in this cartoon. And there is no oxygen available anymore in the middle. And okay, so this is the reason, and I will maybe come back to that later. And just let me tell you that it's actually a success. Oxygen at the center has been measured to be below 1%, and even much below than 1% of oxygen, which is very very low. And here you can see that cells will actually have very different behavior as the cells which are surrounding. So this is one part of the answer to your question. The difference between the exterior and the interior is the amount of oxygen, which is drastically different. Yeah. So growth is outside. And there is the main motivation for these people, actually, from people in cancerology, is to observe cells in such hypoxic condition. The main motivation is to observe them in the core. My motivation and the motivation of the biophysicist. Okay, this is a very interesting point, but my focus, let's say, rather than my motivation, my focus is to understand the ring expansion, which is a slightly different scientific question. Yeah. So, I don't know. I don't know. I guess it will. So I think it's a very good point. We never asked the question, and for the modeling, it doesn't really matter to say what I will have only one signal gradient, which will be oxygen in the model. Sorry? What do you mean? Oxygen is consumed by the cells. Okay, yeah, maybe we can come back to that later. Okay, so this is a ring, and this is the movie you saw after 2 hours. And as you can see, after 2 days, you still have the ring expansion. As I told you, it's a very remarkable pattern, and you can even see it by eyes after a very long time. So it seems to be a very robust collective motion. Still, it's not clear what is the main driving force of this collective motion. So more experimental data. So this is a chemograph. So you look at a section from the center to the exterior, a radial section. This is time. This is space. The distance to the center. So the center is there, and this is time from top to bottom. So initially you see the initial drop of cells, and after some transient time you see this ring with a linear expansion. Okay. And with a constant shape. This is a cell density profile, a section on this axis at several times. As you see, okay, there is some blurring, but it's a very, after nearly a day, it has a very remarkable shape and very robust. Okay, so you would like to have an equation for this cell density profile and maybe more importantly, a formula for the wave. Okay. So this is the first step of modeling is trying to have the players. So our players are the cells and the oxygen. I was a bit reluctant initially because to me it's not completely clear that you can make a sustainable wave with only one signal. So maybe we can come back to that for the discussion. But the answer, it works like this, but it was not completely obvious at the very beginning that you can have something which is really sustainable for a very long time with only one signaling gradient. From my own experience, it was not clear, but this is what is in the model. So depending on the oxygen level, you may have, as observed in the tracking of cell trajectories, you can have several behaviors. So first one, let's say standard, is when oxygen is high enough. This is the exterior, surrounding cells, let's say. And what you observe is unbiased motion, and you have cell division. Then, when oxygen is below some threshold, what is observed is that you have a directional motion, so a biased motion towards the exterior along the gradient of oxygen, which is reasonably strong. So the cells seems to experience something when oxygen is dropping, and they start to move according to the gradient of the signal, which is oxygen. And then something I will totally ignore for the presentation for the mathematical side, and this is the main motivation for the experiment, is what happens when oxygen is very, very low. And what is observed is there is no bias anymore, but motion is very persistent, which means very strongly diffusive. So cells seems to be in a harsh state, and they are really trying to move to find their way out. Let's put it this way. And so you have very strong persistence in motion, but apparently they are not able to read any signal anymore, so there is no bias. Okay, but again, this I will not consider it for the reason that it seems not intuitively it will not contribute to the radial expansion. If those cells are trapped in the core, in the hypoxic region, they will hardly contribute to the expansion, so I will just ignore this part. Although it was the main motivation of the initial experiment. Okay, so our hypothesis is that this collective motion that you can see results from the self-generated gradient, because cells consume oxygen, of course, of a single gradient. So we assume no other signal, and then you have this dichotomy or trichotomy, but I will ignore the third one. If you have enough oxygen, you have cell division, but unbiased motion, which will be put in equation as a diffusion. And if oxygen is low, they will not divide anymore. This is documented in the literature. They need some level of oxygen to divide. And motion will be, in contrast, motion will be biased towards along the gradient of oxygen. And again, we ignore the higher persistence T, which just would be put as a higher diffusion rate coefficient in the hypoxic region. Okay, so before I come to the equation, let me say that this set of hypotheses, these are hypotheses, because it's only experimentally what you have access to is first the cells, then the tracking, what I showed you in the movie, and then it was kind of a tour de force. They could measure simultaneously they could simultaneously observe the cells and measure the level of oxygen by some sensitive films. And they could actually confirm that oxygen is depleted and very low at the core, which again is something which is quite intuitive, but it was made quantitative during the experiment. And before they came to us, they already put everything in a cellular POTS model, which is a kind of individual-based tool, and they could simulate and they could validate the cell density profile and the chemograph. This is numerics, and more remarkably, the parameters were fitted on independent microfluidic experiment. I told you they had this gigantic nitrogen bottle, and they could measure the response of those cells individually in gradients of oxygen with control level of oxygen, and they could parameterize this model, and they end up with so it was very remarkable work they did, but still they were not completely satisfied because first it was very time consuming. It takes days to make such a simulation. Maybe it could be optimized, but yet they were not satisfied. And second, they were hoping for something simpler in terms of modeling to go a little bit further in the interpretation of the experiment. So this is where we came, and again we were lucky to find a simple model and to write the model in a simple form so that you can actually derive formulas and discuss them. This will be the next stage of my talk. So the two questions I will have in mind for the modeling part, the mathematically modeling part, is first, can you really sustain a wave forever in the math part with a single self-geometry gradient? And again, this to me is not completely obvious. And second is the question of growth is interesting because it was not even part in their original model. It was not something they really discussed, and it's something which has been addressed in a subsequent paper by another team on exactly the same experiment, where they claim growth has nothing to do with this collective motion. Okay, it's only a matter of bias and aerotaxis, which is the way cells respond to oxygen gradient. So growth is something I will also keep in mind because to me it's very important. But the question is, how important is it in this problem? Okay, so the minimal modeling framework is always the same thing, just in a different another cartoon, but always the same. You have a threshold of oxygen, which is roughly 1%, let's say, which has been measured, where there seems to be to have a transition where you have division on one side or migration, directed motion on the other side. It might not be sharp. I mean, there could be some overlap. But for today, it will be a very sharp and a dichotomy. Again, the picture is reality is much more complicated than that, but this is the way I will put it. And you have two players: cell density and oxygen concentration. Okay, and this is the model. And you can write a more complicated, very complicated form, saying that the directed part of the motion will depend on the level of oxygen, on the amplitude of the gradient, and many things. But here we will consider that we have only three parameters. So D and R are already known. D is the diffusion coefficient, and R is the rate of growth. And then I will have a third coefficient, which will be the advection speed of aerotaxis. Which is to say that when oxygen is low, collectively, in average, the cell population will move at this speed, and it will perfectly follow the direction of the gradient. So it's just a constant speed And in mathematics, I just say that it's proportional to the sign of the gradient. So there is whatever is the amplitude of the gradient of oxygen, whatever is the shape of this oxygen concentration profile, the speed of migration will be the same. The only difference will be whether oxygen is large or low to activate this migration phenotype. So it's very simple. The reality is more complicated than that. But doing that, it's possible then to decipher different mechanisms. So then I have two lines in my model with in brackets. Either oxygen is large enough, so C0 is a threshold, 1%, and then I have diffusion with, let's say, small diffusion coefficient and growth. This is R rho. So this is exactly my Fisher equation, except that it's not density dependent, but it's oxygen dependent rate of growth, but it's exactly the same, more or less the same. And if oxygen is below some threshold, then I have directed motion and no growth. So this is the go or grow hypothesis, that you have either growth or biased motion, depending on the level of oxygen. Okay, go or grow is not our idea. It was coined by in a paper by Adi Kiru et al. About brain tumor expansion, but in their model and in subsequent model, it's about a density-dependent switch. The switch between division or migration depends on the density, on the local number of cells. Whether in our case, it depends on the level of oxygen. But apart from that, it's the idea that you have different phenotypes and you have a switch between the different phenotypes. Okay, and then I need an equation for the oxygen level, which is simply a diffusion of oxygen, which is a large diffusion coefficient, sorry, and cell consumption. So there is a law of mass action saying that you need cells and oxygen to consume, to deplete oxygen concentration. Okay, so what is interesting with this model is that if you look for a wave, so now the question is, do you have a wave? So a wave, what is it? It's you need to find the speed of the wave and the profile. The question is, do we have a particular solution which is of the form rho of x minus sigma t, where sigma is the speed, and rho is a profile which is stationary. So we are looking for something which is moving in space at some speed. Yeah. It's a 1D, and it's more than that. It's 1D, and it's from the center, which is at minus infinity. This will be the core, the center, to the outside. And I'm thinking of something which is in between, which is my ring, and which means that this sign will be +1. I have in mind exactly this picture, where you see whatever the shape of this concentration profile, it just tells to the cell to move to the right. So in fact, yeah. It's a good point, and it was a subject of discussion. But my point is that it's not very important. The curvature, it's not quite important. Of course, you have a dimensional scaling. If you increase, the number of cells in the ring will increase, because the shape of the ring, the width, will be constant over time, or nearly constant. Yeah. So to me, this I don't. So you're totally right. My feeling is that it's a secondary effect. Yeah, yeah. Yeah. There is growth, but as you tell, if you look in the correct thing would be to do a radial, a 2D radial model with the radial diffusion and so on. But I think if you do that, you will get essentially the same conclusion. Yeah. Oxygen is fixed at plus infinity at 21%. Yes. Yes, yes, yes. You have oxygen far away at 21%. Actually, oxygen diffuses very fast. So ahead of the ring, it's already only 3 to 6%. Okay. Ah, no, 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 no. No, 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 it's the layer is a 1 or 2 cell width. It's very, very narrow. Yeah. Actually, yeah, yeah. No, the oxygen will evolve because the ring is progressing. So yeah, one way to answer your question is that it has been measured experimentally that if you follow the ring, the concentration of oxygen at the ring is constant. Yes, 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 yes. So one very important thing telling you about this self-generated gradient. Something I'm very interested in this kind of problem is that, of course, here you are looking for the wave density, but of course the environment has to move at the same speed. The two things are moving together, and this was measured. They measured that the concentration of oxygen is constant at the ring. So it's really something on the oxygen signal information on the cells are moving at the same speed. Okay, so what is interesting to this problem? To me, why it is simple and why it's you can go a step further is that if you put yourself on one side or the other of the threshold, you have something with constant coefficients. Either you have a diffusion speed at a constant speed because this sign will be +1, as I said, they just read the direction of the gradient of the signal, and 0, or you have diffusion and growth rate. So it's only about linear equation for the cell density. Of course, this one is non-linear because of this product, but this one is linear, and by something we don't quite understand yet, you make computations. It's just a matter of exponential solutions because it's linear equation. You have exponential solutions. You have to match the two because at the transition threshold you have to match your two exponential. But when you do the matching, you get the speed of the value of the speed. So for this model, we claim that the spreading speed is this formula. We'll discuss that later. But what is quite interesting is that it does not depend on the oxygen, on the shape of the oxygen consumption or diffusion, on the details of oxygen consumption or diffusion, for the good reason that it just reads the level of oxygen and not its shape. Okay. Anyway, you have something which is quite simple because of a linear, it's a piecewise linear model, and you get this value for the speed. So you have two cases. Either this aerotactic speed is small, and small compared to the same speed as we have seen at the very earlier in the talk, this root of RD, which is the speed of reaction diffusion and growth diffusion equation. And if it is small enough below this threshold, you get the same speed as before, which means that it's exactly as if there were no aerotaxis. Of course, there is aerotaxis that shape the cell density, but regarding the wave speed, it has no influence. And if advection is large enough as compared to this reaction diffusion speed, then you have another formula. Now you can check that they coincide at the threshold. Okay, so what now the question is to read out this formula and what does this tell you about the underlying mechanisms. So first, what you can see is that growth, I told you that growth is important to me, it contributes to half of the speed when you are at the transition. So at the transition, this is the case where you have equality here. So it means that this A is half of it. And if you decompose this weight, it might be clear on this, in this formula. Here you see that you have a contribution of advection and speed, and growth, sorry, to the overall speed. And at this threshold, this is one thing, and this is the same. So you have twice the same quantity. So in fact, it means that growth, to me, contributes to half of the speed when you are at the transition. And then if you increase the advection speed, let's say, or which should also call the aerotatic bias, then the growth will have a smaller and smaller contribution. You see that if A increases, this one will increase, this will decrease, so the contribution of this part, which is essentially due to growth, will diminish. And for the experimental values, in fact, this is less than 10% on this one. So it's very small contribution of growth to the overall speed of collective motion, which makes sense. I mean, it's really this very strong bias of cells in hypoxia that makes the collective ring. So growth is not that important. Okay, this is the first conclusion of this formula. If A is large enough as compared to that, growth has a limited contribution. But something you can do before computing the value of the speed, you can look at the equation in the moving frame. So this is the same equation written in the compact way in the moving frame, which is x minus sigma t. So you put yourself in the correct frame. You have this equation. You integrate. And if you integrate, you have growth on the right side. So you have the contribution to growth. It's only on the right side of the threshold. And it tells you essentially that for each unit of time, you have a number of new cells due to this growth with constant rate. And on the left side, because it's a conservative equation, you get the flux at minus infinity, which is sigma minus A times the number of cells which are at the back, the cells which are trapped. And you see that sigma has to be, so this is positive, so sigma is larger than A. So it means that the collective speed, sigma is the speed of the ring, is larger than the advection speed. Something you can of course see on the formula, but even without the formula you can see that. And this tells you that it's okay, the wave moves faster than individual cells, which again makes sense. But at this stage, it was not completely clear for biophysics that it tells you that, and the reason that the wave moves faster is due to growth. In fact, you have some little contribution of the growth that makes the wave expanding, and that create this collective speed. And our main conclusion is that growth might not be significant to the wave speed, as I told you before, but still, you need growth to sustain the wave propagation. Okay, if growth is 0, there will be no mathematical way, and you will see essentially cell dispersion. And growth is important to have a wave for a very long time, as in the experiment. And now for this formula, you can somehow describe what will be the typical life of a cell. So according to this formula, and this you can see also on the if you now look back into the data, and this is what you can see. So you will have the ring. Oops. So you have the ring expansion. So you have the transient regime, but in the long time regime, you will have cells at the edge. They will essentially divide, and a new cell will be created. And if you follow this cell, what will happen? It will move slowly, and at some point the ring will come. So it will be inside the ring, and it will start moving due to this bias. So it will try to follow the ring, because now the environment is moving, and it will try to keep pace of the environmental change. But as you see, in average, it moves slower than the collective speed. So whatever, the ring will overpass, and after some time, the cell will be trapped behind, and at this point, it will be so in the moving frame, it will be sent to minus infinity due to this flux A minus sigma in some sense. So this is something where you see that the wave is a kind of equilibrium between growth aerotaxis and cell flush or cell leakage at the back. And interestingly to me, so this seems to be very intuitive, and it seems to be you don't really need a model to say that. And if you look at the data, you can see that the cell, there will be a net flux from the exterior to the interior, and you will see that cell will spend some time in the ring, but after some time they will trap back. But there was a paper published a year after the paper we collaborated in, and they claim that growth has nothing to do, and growth is not there, and you cannot say it's of any importance. And then there will be some commentary, some discussion. And I think for me the main importance is that it's clear that it's not significant for the overall speed, but still it's an important ingredient to have something that is sustainable for a long time. Yeah. Where do you see non-linearity? So you have parentheses there. Ah no, there is no row here. So this one is a typo. I should have removed this one. Sorry about that. And for experts, but I will be very quick on that. There is a nice connection with reaction diffusion equation, where about this transition between pooled and pushed wave. For those who know, in reaction diffusion equation, wave like this one can be either pooled. So pooled means is that all the dynamics is described at the way the cell density, the cells or the population density which is at the edge. And so those ones are, let's say, dividing and pulling the wave and making the dynamics. Or it can be pushed when you have a net growth in the bulk, and this send cells to the edge, and this create a kind of a different dynamics. Anyway, we have exactly the same transition here, depending on this threshold. And if you have a small bias, it means that you have strong division, relatively strong cell division. It means that essentially all the dynamics are created by those cells which are dividing at the edge. And in this case, you can see that it only depends on what happens at the edge of the wave, because the speed does not depend on the advection. So it's a clear way to say that it only matters for the wave speed that division and diffusion at the edge. But on the other case, of course, there is a net transfer from the bulk, and the wave is pushed by cells at the back. But still, the cells will be flushed out at the back. So it's but there is a exchange between the bulk and the edge. Anyway, and okay, so this is to say that this is what happens with the numerical simulations of the cellular POTS model. So exactly what I presented before. And finally, some very mathematical reasons. So it's a difficult problem because there is no comparison principle for experts. But it's possible to say something which is weaker than saying that for any initial data you will see the wave expansion at this speed. You have this kind of weak result by Mete-Dimer-Sigil. And it's possible to have a simpler model for which you can rescue some comparison principle. And this is why you replace the oxygen threshold by saying that the threshold x of t is a location where you have exactly one unit of cells on the right side. It's a kind of it's similar to rank-based interaction in finance, where particles are interacting with respect to their rank in the line. So here you say that the threshold is where you have that many cells on the right side of you, and if you are on the left side, you will start moving. Okay, and my conclusion is that, so to me what is important is to understand this long-lasting traveling wave, which was not completely obvious because of cell leakage. So it means whatever you do, you are losing cells at the back, and in this specific case, this is sustained by this compensated by the fact that you have new cells created on the right. So it's this equilibrium between new cells and cells which are trapped or flushed in the moving frame that make this wave collective motion for a long time. And this belongs to a wider class of models of self-generated gradients, which are studied by several teams, and in particular this team by Insal, Robert Insal, and his collaborators. They have published a series of papers, advocating for promoting for self-geometry gradients, saying that it might be more, let's say, more so something people should seek in developmental biology should be more present than expected for many conceptual reasons. Think that you don't need a long-range chemoattractant gradients. You can just rely on what is close to the cell population, because the population is making its own gradient along the journey, so that they will experience the same environmental conditions. So which one problem with pre-pattern gradient is if you have to cross a long distance, you need a very shallow gradient to do that. But with this problem, you can shape the gradient across the journey, and it's supposedly better robust for the developmental system. And I will conclude with one picture from this science paper where they have put Dictyostelium, the same cells, but for different purposes, into a labyrinth. And the color code is the time, and the cell were able to resolve the maze. And they claim that it's because they are making their own gradient across the way, and doing that they can read out, in some sense, the complex geometry of the environment and find their way out. So this is just one picture, but we have a series of papers very interesting about this idea of gradients. Thank you very much.